Yeah, good morning to all of you. In this lecture, I am going to discuss the concept of electric potential. What is electric potential? What is electric potential difference? Relation between electric field and potential. And I will also solve few examples based on this electric potential concept. Means how to calculate the electric potential in different situations. So the first question is, what is electric potential? So electric potential at any point is simply the how much work done by the force in bringing the unit charge, which is test charge, from infinity to a reference point. So this is the simple definition of electric potential, and mathematically it is expressed as electric potential V is simply minus E dot dl, where E is electric field and dl is a length element, which is in Cartesian coordinate system dx I cap, dy j cap and dz k cap. And next we have this E is electric field, dl is a length element which can be expressed as dx I cap, dy j cap and dz k cap. It has different profile in different coordinate system. In Cartesian it has this profile, and we have a different profile in spherical and cylindrical coordinate system. Next we have a electric relation between field and potential. Electric field and electric potential. So electric field is simply minus del V, means negative gradient of potential. So electric field is simply is gradient of potential, and this del is a mathematical operator. So we can, and this is the relation between field and potential. So we can express electric field in negative gradient of potential, and we can express our, with this expression, with these two expression, we can conclude that we can find out the electric field for a given potential, and the converse is also possible. For a given field we can find out the potential, and this del is a mathematical operator. This is known as del. This is simply a mathematical operator. Again, it has, like this length element, it has different profile. This del in Cartesian is simply I del by del x plus j del by del y plus k cap del by del z, or, and this E is also written as minus grad of V. This V is potential and this is grad of V. So in Cartesian coordinate system, this mathematical operator del is expressed as I del by del x plus j del by del y plus k del by del z. We have different profile. In spherical coordinate we have different profile. In cylindrical coordinate system we have different profile. So this is the way to define the electric field, which is negative gradient of potential, and we can also define the electric potential difference. So one more information, if the field is expressed in this way, so which means E is negative gradient of potential. So this is the relation between field and potential. Now electric potential difference. Let me just erase. So electric potential difference. If we have a situation like this, if we have a 2 point in space, this is x, y and z. So let's say this is point B and this is point A, and distance of this point is this, and this is RB, this is RA, and this is the path. So this is simply the line integral. So the potential at point A is VA and potential at point V is simply VB. So the difference of potential is known as electric potential difference. So VB minus VA, which is simply E dot A to B dl. E dot simply dl. So this is the way to define the electric potential. If this loop is closed, like that, A to B. So for a closed loop, and this integral is simply line integral. For a closed loop, we have this integral E dot dl is equal to 0, and this is line. So for a closed loop, this E dot dl is 0, which means line integral is independent of path. So this is just a information about the electric field lines, that line integral is independent of path. So this is path independent integral. And if you, this is line integral, if you take this can also be written as del cross E. This is the integral form. So from this integral we can also find out this expression, because this is line integral. So using Stokes theorem, which establishes the relation between line and surface integral. So using Stokes theorem, this line integral changed into surface integral. So we have del cross E equal to 0, which tells us, so in electrostat, del cross E is equal to 0, which means field lines, electric field lines never curl. It only diverge or converge through a point in a question. So this is very important information about the electric field and field lines in electrostat. So one can say that, or we can say that in electrostat, work done is independent of path, and electric field line never curls. It only diverge or converge through a point in a question. That is why curl of E is 0. And in another way we can say that for possible electrostatic field, for electrostatic field, curl of E is 0. And for impossible electrostatic field, if del cross E is not equal to 0, which is impossible, electrostatic. So these are very important information which will help to solve the examples. If someone asks, check if we have a profile, if we have a profile of electric field, some 2x I cap plus 5y j cap plus xy square z k cap, and we have to check whether this field is possible electrostatic field or not. So what we have to do, we will simply check the curl of E. If curl of E, and this E has any profile, whether it is in Cartesian or spherical or cylindrical profile, we have to simply check the curl of E. If the curl of E is 0, then in that case the given electric field is possible electrostatic field. If the curl of E, whatever be the profile of E, the curl of E not equal to 0, the curl of E not equal to 0, in that case that field is not a electrostatic field. It is field, but so in this, with the help of this expression, we can identify we can recognize whether the given field is electrostatic field or not. So this is the another way to analyze the concept of electric field and field lines. So electric potential due to a, next we will discuss the electric potential due to a point charge. So electric potential due to a point charge. So electric potential due to a point charge is simply 1 upon 4 pi epsilon 0 point charge Q. If the point charge is Q, then this is R. This is for single point charge, and this is the profile of electric potential due to a single point charge. Now if we have a system of charges, if we have system of charges, in that case electric field is simply 1 upon 4 pi epsilon 0 Qi upon Ri. For a system of charges, we have and these charges are discrete charges. In that case, we have the electric potential profile is this. If the charge is discrete, for discrete charge system, for discrete charge system means we have a charge like Q1, Q2, Q3, Q4. Now if we have if the charge for, what is the profile of electric potential for continuous? So this is for discrete and this is for continuous. So for a continuous charge system, which means if the charge is distributed along the wire, means in 1D, if the charge is distributed along the surface, if the charge is distributed throughout the volume, in that case I have already discussed these concepts in the electric field lecture, in which we have already derived the expression or written the expression of electric field or force corresponding to discrete and expression of force and field corresponding to discrete and continuous. Similarly, we have a potential profile for a continuous charge system. So in that case, the potential, if we have a single point charge, so V for this is 1 upon 4 pi epsilon 0 dq by r. This is simply the profile of electric potential for a continuous, and this is the difference between summation and difference. Summation is correspond to the discrete charge system, means we have a charge Q1, Q2, Q3, Q4, and if the charge is distributed continuously throughout the line, throughout the surface, throughout the volume, then we have to follow the integration. So now, depending upon the situation, this dq has different profile. This dq is simply lambda dl. This dq is simply sigma dA. This dq is simply rho dV. If the charge is distributed along the line. So we have a concept of line charge density, which is dq by dl. If the charge is distributed along the surface, if the charge is distributed along the volume, then we have volume charge density. Then we have a volume charge density. So this dq is lambda is line charge density, which is dq by dl, and this sigma is surface charge density, which is dq by dA. This volume rho is volume charge density, which is dq by charge per unit volume. So depending upon the situation, for a continuous system, we have three different profile of force, field and potential. So if the charge is distributed along the line, then we have potential profile 1 by 4 pi epsilon 0 lambda dl by r. If the charge is distributed along the surface, then we have potential profile V equal to 1 upon 4 pi epsilon 0 sigma dA by r. If the charge is distributed along the volume, then we have potential profile 1 upon 4 pi epsilon 0 rho dV by r. So this is the way to define or to express the profile of potential in different situation. For a point charge, we have this profile. For a, if this is for a single point charge, if we have a system of charge, then we can use integration sign. If the charge is not discrete, it is distributed continuously, then we have this integration profile, and this dq is, and depending upon the nature of distribution, whether the charge is distributed along the line, surface or volume, we have different profile of dq, and corresponding we have different profile of this potential. So it's all about the concept of electric field and electric potential and potential difference. So next we will solve the examples. Based on this, let us analyze the actual concept of potential in terms of example. So if we have a charge, now if we have this situation, suppose we have a square, this is A, this is B, and this is C, and this is D, and Q charge are placed at A and B, So given that, so in this figure we have this information. We have a square whose sides, so this is just an example to understand the concept of electric potential, that how to evaluate the electric potential in this situation. So a charge Q placed at the corner A and B of a square whose sides are A, as in shown in figure. Then find V at C and D. So this is the information that we have. This is figure whose sides are, we have a square whose sides are A, and Q charge are placed at A and B. Means Q charge placed at corner A and corner B, and we have to find out the electric potential at C and D. We have to find out. So this is the problem, or this is the example. So we have to find out electric potential at C and D. So solution means we have to find out the electric potential at this point is simply Vc, and at this point is simply Vd. So what is Vc? Vc is, so electric potential at this point C due to this charge. Electric potential at point C due to this charge, because these are point charge. So let me just redraw. So this is Q, this is Q, this is B, this is C, this is D, and this is A. And the distance A, A. What is this distance? This is A. So this is root 2a. I hope it is clear to all of you that this distance is root 2a, square of under root square of this square of this. So this is the resultant. So potential at this point C is simply the potential due to this charge and potential due to this charge. So potential due to VAC plus potential due to, this is a scalar quantity, and potential also follow the law of superposition, and we have already, I think in lecture 1 we have already explained the concept of superposition, which is the experimental fact. Principle of superposition is an experimental fact. This is not a logical necessity. So this is just a BC. So what is potential? What is VAC? VAC is simply 1 upon 4 pi epsilon 0 Q by R square. AC, Q by simply AC, and which is 1 upon 4 pi epsilon naught Q by root 2a. And what is VBC? This is again 1 upon 4 pi. We know the potential profile, potential due to a point charge is simply 1 by 4 pi epsilon 0 Q by R, and R is the distance. In this case, BC is, in this case our R is BC, BC is a square of this side. In this case, from C to A, the R is AC. In this case, our R is AC, which is root 2A. So 1 upon 4 pi epsilon naught Q by BC, which is 1 upon 4 pi epsilon naught Q by root 2A. Now adding these two, what we have? VAC plus VBC, which is equal to Q upon 4 pi epsilon naught taking root 2a. So this is simply 1 plus 2a will cancel out, and what we have, let me just rewrite 1 by, this is simply, so BC is simply A, not 2a. This BC is distance from C to B is A. So this is A, and what we have, 1 by root 2a plus 1 by A. So this is the way to find out the potential. Similarly, we can find out the potential at this point. If you draw this point, let me just, and this is again root 2a. This distance is again root 2a. Root 2a. So potential at this point we can also find out, means this is the general problem. We can, with the help of this problem, we can understand the concept that at any corner we can find out the potential due to this square loop if the charge q placed anywhere. If the charge is placed at any corner of this square, we can also find out the potential if the charge is placed at the center of this square. We can find out the potential due to not only square, we can find out the potential due to if the charge is placed at the center of a cube or at one corner of a cube. So there are n number of ways to find out the potential in different situations. This is just one of the way to analyze the potential concept. So we simply find out the potential due to this. We can find out the potential at point D. So which is VD. Again, this VD is simply potential due to this BD plus AD. In this case, we can, if you want to find out the potential at point D, then which is VD. So VD means we can find out the potential due to at point D due to B at point D due to this A. So this is VA and VAD and VBD. And what is VDD? VBD is again Q upon 4 pi epsilon naught. Is simply VD is again root 2A. So 1 upon root 2A. And VAD This is simply VAD. What is VAD? VAD 1 upon 4 pi epsilon 0 Q by R. R is in this case is R is A. So simply this is Q upon 4 pi epsilon naught A. We can take Q upon 4 pi epsilon, this is D, which is 1 by root 2A plus 1 by A. So it's all about this example. So we can find out the electric potential at any corner of this. If charge Q placed at any corner of this square whose sides are A. Thank you.